Yes, your screen is visible.
Is it working?
Yeah.
Yes, yes. So you can go to your full screen mode. Want?
Right. Okay. I'm just. I don't normally use Google Meet, so this is all new to me. I'm just trying to learn along. I am presenting for everyone. That's correct.
Yes.
And then full screen. Did you say? Okay.
We don't see full screen yet because I think when you're sharing it, share it as
Yes.
entire screen. Share it as your
Right.
entire
Okay.
screen. So
Okay.
when you unshare it, and then you can share as an entire screen.
Right. I will try that again. I think it might be screen 2. Any good now?
Yes, it is. Screen is visible. If you go to full screen mode.
I did that.
It is not at full screen.
Right. What I can do then? That's not the one.
Sharing it, share it as an entire screen. So there will be an option.
Right. Okay.
Sharing
Maybe. Right. I will. I can see it from here, but for some reason it isn't working. Right. Right. Hello.
Hello, entire screen. Yes. Share your entire screen.
Right. Entire screen. This is screen 2.
Your presentation is visible now.
Yeah, but still,
when you go
it's not the full screen.
When you click on full screen from beginning.
Yes. I mean, what happens when I click full screen? I can see full screen on. I have 2 monitors.
Okay.
But you are not able to see the full. Are you able to see the full screen now?
No.
No.
So
right.
Maybe we can then present as this.
Yeah, I'll try one more time. Let's see whether if it works this way. You don't see it yet? No. Right. I think it's my monitor playing up.
So I think
rather than
we can go with that mode without full screen. Presentation mode.
What's another one?
Sorry, what?
No.
Yeah, you can quit for a while and rejoin. Well, that should work.
Do you think it will work?
No.
Yeah, hope so.
Right. Maybe if I drop this into here. How does it work?
Yes, it is full screen.
You can see that now.
Full screen,
Right.
yes.
Okay. Good.
So,
Good.
so yeah, shall we get started? Hello, Russell.
Okay.
Yeah.
Yes. So
I'm
I
ready.
think we'll get started.
Yeah, please.
A very good afternoon.
Hello.
Yes. Are you able to hear me? I wasn't able to hear you. Sorry.
Affordable and clean energy IIT Harvard. I am Professor Prof Venugopal. I take this opportunity to.
I think.
Yeah, hope I'm audible.
Dr.
I'm sorry.
Yes.
Yeah, I should be audible now. Yeah, okay. I heartily welcome Professor Vengatesan Venugopal who holds the personal chair in ocean engineering in University of Edinburgh. He is the head of the Institute of Energy Systems, which is one of the 7 research institutes within the School of Engineering at Edinburgh University, Scotland, UK. Before I formally introduce the speaker, I request Professor Dheeraj Patil, Department of Mechanical Materials and Aerospace Engineering, IIT Harvard, to welcome the guest and introduce the Global Center of Excellence in Affordable and Clean Energy. Professor Dheeraj. Yeah.
Am I audible?
Audible. Yeah.
Yeah. So I briefly introduced this center, which we call a Global Center of Excellence in Affordable and Clean Energy. This center is committed to United Nations 17 Sustainable Development Goals, and goal number 7 is clean, affordable, and clean energy. The center is committed to provide laboratory facilities, upskilling, research and development, as well as outreach.
Professor Dheeraj, we can see your screen.
Can you see my screen?
I can.
Yeah. Okay. So hackathon and challenges. We are going to come up with innovation and incubation support. We have a grassroots implementation partner, which is a Selco Foundation with this center, and they have field level experiences. So with them, we will be able to have the field deployments and field mentorship and guidance. The center is currently establishing.
Professor Dheeraj, I'm sorry, there's some difficulty in hearing your audio.
So center is currently establishing the lab equipment, test and measurement lab equipment, fabrication lab, skill development, R&D lab, and field testing lab. The mission at the center is to make affordable and clean energy as a backbone to India's development. As I said, we are going to provide the laboratory facilities, and we are going to create a platform to design and engineer affordable, energy efficient, and renewable energy products to enhance the livelihood of the poor. The center is committed for mentorship, incubation, and the innovative ideas. To improve the energy efficiencies of the appliances which work on the green energy. In the phase 1 of the project, which just started, we are in procuring and installing these equipments, as I mentioned, and to increase the visibility of the center through outreach programs and to facilitate problem identification via outreach. The center has been inaugurated on 28th of January 2022 by Principal Scientific Advisor, Government of India. The program was presided over by our Chairman, Board of Governors, IIT Harvard. And we started this Trees talk series, which is basically talks on renewables, empowering Earth and sustainability. We have been having, we had a total 4 talks so far, and this is a 5th talk. The 5th talk is by Professor Venugopal from University of Edinburgh. Currently, the equipments available at the center are listed here. We have an automatic weather station. We have power hardware in loop, simulator, for R&D purposes in power electronics. We have skill development equipment on flat plate solar collector, thermal energy collector, solar array simulator, wind energy training system. We have a lot of fabrication equipment like welding machine and sheet metal cutting machine, bending machine, as well as compressor and power tools. So I welcome all the people to contribute to the center's development. You can contact the center at office.ace@iitdh.ac.in and fic.ace@iitdh.ac.in. So thank you, and over to Professor Prashant Revankar for the introduction of the speaker. Thank you, Professor Venugopal, for accepting this invitation to talk for the center. Thank you.
Thank you, Professor Dheeraj. It's my immense pleasure to introduce the chief guest before inviting him to talk on the topic titled Ocean Renewable Energy Technologies for Achieving Sustainable Development Goals. Let me briefly introduce the speaker of today's session. Professor Vengatesan Venugopal received a Bachelor of Technology degree in Civil Engineering in 1991 from Pondicherry University, India. Glasgow, United Kingdom. He has been the postdoctoral fellow for from 2000 to 2005 at Herod Watt University, Edinburgh, UK. Professor Venugopal joined the University of Edinburgh as lecturer in ocean renewables in 2005. His research interests include numerical modeling of wave and tide propagation in ocean and bay scale, physical modeling of wave and tides in laboratory and their interactions with offshore energy structures, wave and tidal power resource modeling, arrays of wave and tidal energy devices modeling, interaction of wave current turbulence modeling, analysis of extreme waves, offshore floating wind turbines, climate change modeling, environmental impact modeling of energy structures, breakwaters, and ocean wave tidal current statistics. He has been principal and co-investigator for several research projects which are valued at £20 million funded by the Scottish Funding Council, Health and Safety Offshore Division, Engineering and Physical Sciences Research Council, EU FP7, ICARI, British Council and United Kingdom Industries. He has supervised 15 postdocs, 32 PhD researchers, 7 engineering doctorate researchers, 1 MPhil and 1 MSc by engineering, MSc by research. Professor Venugopal has published more than 180 peer-reviewed journal and conference articles. He is also a chartered engineer and fellow of Institute of Mechanical Engineers. So here I present Professor Venugopal to deliver his talk on the ocean engineering. Sir, would you please share your screen? And we would like to inform the audience that they may post their questions in the question and answer box. Venugopal, sir, you could please take over.
Thank you, Professor Prashant, for the introduction. And also I would like to thank you, Professor Dheeraj, for inviting me to give this presentation. It's my pleasure to be here. And even though I can't see everyone, I believe you can see me. As said in the introduction, I'm joining from Edinburgh. Edinburgh, it's raining here. It's 7 degrees, I believe, today. And Professor Dheeraj, you've been here, so you know how Edinburgh would be. You would see a sunshine for a few minutes and then rain and then wind. You can see all the weather climate within a day or within a 10 minutes time. And I hope you are all safe and in India. As you can see that I'm joining from my home today. We are still working from home and we have the freedom of going to office or work from home, but advice is still to work from home. And if you are not able to hear my voice clearly, or if anything is not clear to you, please stop me and I will try and repeat it. And hope you can see my presentation well. Is that the case? Can I confirm with someone
Yes.
that you can see me? Okay,
Yes.
right. Okay, so I'm here as was given in the introduction. I'm here to deliver a webinar on ocean renewable energy technologies for achieving the Sustainable Development Goals. And what I'm going to do, I'm going to introduce the university. Then I'm going to talk about some fact about ocean renewable energy, which covers basically waves, tides, and offshore wind. Then I will move on to talk about my own research. We know that the time is only 1 hour and we have already lost 20 minutes. Not lost is not the right word. We are delayed for 20 minutes. So therefore, I have a feeling that I need to rush. But again, as I said, please stop me if you are not very happy with any slides, and then I can repeat it and give you the information again. So let's see if it works right. So if you look at the slide here, it talks about SDG 7. And this is about this goal. 7 is about affordable energy and clean energy. As the text goes, this goal is to ensure the access to affordable, reliable, sustainable, and modern energy. If you manage to read the UN report,
I am sorry.
Yes.
The transparency, why I am seeing very small, is it only for me?
No, sir, it's visible, sir. It's visible.
It is just visible, but very small in the middle.
Sir,
Okay, please
pin it,
continue.
sir. You have an option to pin it, sir. You can pin it. Click on that. You can pin it, sir, so that it will appear as the main screen. You have an option to pin it, sir.
Sorry, please continue.
Yes.
Thank you. The UN report says the world is making progress towards goal 7. That's fine. And access to electricity in poorer countries has begun to accelerate. Energy efficiency continues to improve. Renewable energy is making impressive gain in the electricity sector, and so on. But if you also read another point, which is to say, nevertheless, we need to focus our attention to improve access to clean and safe cooking fuels and technologies. It's talking about the last word, technologies. That's what we are focused at Edinburgh. We are developing technologies or helping to develop technologies which will be put in the ocean to harvest ocean energy, so that we will also be contributing to renewable energy. That's where our research comes into play. Just to talk about Edinburgh University, what you see here is a sunny day. If you come to the central campus of Edinburgh University, this is how it would look. And I'm not sure whether Professor Draj, you managed to go to this place, the central city center?
Yes, I did went there.
Okay, good. So the Edinburgh University was founded in 1583. It's more than 500 years old. And this is supposed to be the 6th oldest university in the English-speaking world. And we are consistently ranked one of the top universities in the world. And 100% of our departments are conducting world-leading research. Again, some more information about our university. We are one of the largest universities in the UK. We have more than 23,000 undergraduate, 12,000 postgraduate, and 44% of our students are from overseas, international students, and they come from more than 180 countries around the world. We are consistently topped or ranked 50, just within 50 in the world. And we were placed in the 16th rank in 2020 QS World University ranking. We are first in Scotland, 4th in the 2014 REF exercise which is an exercise conducted in the UK to rank the universities based on their teaching. Mostly it's based on the research capacity. And 83% of our university is classified as world leading or internationally excellent. And within our university, we have 3 colleges of arts, humanities, and social sciences, College of Medicine and Veterinary Sciences, veterinary medicine, and College of Science and Engineering. I belong to College of Science and Engineering. And Edinburgh has produced 21 Nobel Prize winners so far. There were also other 5 Nobel Prize equivalents, such as the Abel and Turing Awards. So it is a university to remember. 21 Nobel Prize is not an easy thing to do. And we have also produced distinguished alumni in the past. And the picture you see on the right-hand side, this is where the convocation, the degree awarding ceremony would take place. And the people that you see on the left-hand side would have gone through the doors to this venue where they would have been graduated with some different degrees. Some of the notable alumni are, if you read the name Charles Darwin, you would have heard about him, and David Hume, and recently Gordon Brown, our former UK Prime Minister, James Clerk Maxwell, the physicist. The electrical students would have studied about Maxwell theorem and so on. Sir Walter Scott, the writer, and J.K. Rowling, the Harry Potter story writer. And the list goes on. It's good to have these alumni attached with Edinburgh universities. Let's look at the links with India. The first book on trade with India, written by then Edinburgh University principal, Professor William Robertson, in 1791. In 1875, Indian students at Edinburgh, they set up the first Indian association in the UK, which is the first South Asian association. And Sir Prafulla Chandra Roy, he is regarded as one of the father of chemical sciences in India. He studied and got his PhD from Edinburgh University in 1887. One of the alumni include Dr. Kadambani Ganguly. She's one of the female doctors in India, first female doctors. And Maharaj Bhagwat Singh Ji of Gondal, he studied medicine in 1895. So these are all some of the links with between Edinburgh and Edinburgh University and India. And you could see many bullet points there. And this is just to say that we have research partnership with Indian institutes. There are many industry are also included, but in particularly, we have had research collaborations with most of the IITs. When I left India, there were only 5 IITs, and now I think we have 23 IITs. And we have managed to keep the relationship going with IITs, at least in my case. I worked with all the old 5 IITs. And we also produced, or we were partners in a large number of UKRE projects. And the community, we have just about 500 Indian students and 200 visits to India by our staff every year, but not in the recent 2 years, but pre-COVID conditions. Many staff here often visit India. And you can see the other information given there. We have Center for South Asian Studies. We have Edinburgh Institute, India Institute, which was organized, inaugurated by the late Dr. Abdul Kalam. And you could see him when he visited Edinburgh University. He did a presentation at the university during the inauguration. And let's look at College of Science and Engineering. So if you recall, I've said there are 3 colleges within the university. And the College of Engineering and Science, it has 7 schools and 30 research institutes. And we have more than 2,000 staff and 8,000 students attending College of Science and Engineering. It covers biological sciences, chemistry, engineering, geosciences, informatics, mathematics, physics, and astronomy. That's the major field of teaching and research we do under College of Science and Engineering. And the University of Edinburgh has a very large research and development capacity. There are more than 300 internationally excellent expertise are working on energy-related subjects. And I'm not sure whether you will be able to read them on the table on the right-hand side. It covers engineering, geosciences, informatics, maths, and we cover anything from solar to ocean energy to carbon capture to fossil fuels, smart grids, energy materials, energy storage, energy law and carbon auditing, and that kind of everything related to energy systems. And if you come to School of Engineering, the School of Engineering has 4 disciplines: civil engineering, chemical engineering, electrical and electronic engineering, and mechanical engineering. Even though I'm a civil engineer, but I teach in mechanical engineering. That's the flexibility we have. You don't need to be a civil engineer to teach a mechanical engineer or vice versa. We have 7 research institutes: bioengineering, digital communications, energy systems. That's where I work at. Infrastructure and environment, I think that's where Professor Draj was placed when he was here. Materials and processes, micro and nano systems, multi-scale thermofluids. So these are all the 7 research institutes we have within School of Engineering, and we conduct a serious amount of research under these institutes. And 94% of the research we conduct are classed as world leading or internationally excellent. Now I'm going to take you to my own institute, which is the Institute for Energy Systems. The aim of our institute is to conduct low and zero carbon production of energy. Probably the low is going to disappear very soon. It will become zero carbon production of energy very quickly. We have 31 academic staff, which they are consisting of Chancellor's Fellow, lecturers, senior lecturers, reader, and professors. And we have 28 postdocs, maybe more than that. The last time when I counted it was 28. Now it would be more than 30. And about 70 PhD students and engineering doctorate students. And our expertise are listed here. We do resource modeling and measurement. Resource modeling means this includes wind, wave, tides, and solar, and so on. And we have expertise in hydrodynamics, aerodynamics, computational fluid dynamics, thermodynamics, and we have research colleagues working on energy storage, electromagnetics, power electronics, control, power systems and analysis, life cycle assessment, policy and innovation. So these are all the key areas that we work on and do our research. And we operate on the following research themes: clean combustion engines, electrical power conversion, energy policy, economics and innovation, energy storage and carbon capture, energy and climate change, naval architecture, offshore renewable energy, power system and smart grids. So if you look at our research themes, it covers basically what I have just listed. And I don't think another 30 minutes would be sufficient for me to explain everything that we do here, but this is for you just to note down. These are all the research themes that we operate on. What we mainly do here, we develop resources, which will involve numerical modeling and physical measurements. Then we develop technologies to capture the resources, and then develop technologies to convert them, and then to deliver them. So this is what we basically do within our institute. And the resources would be If you look at the bottom boxes, they cover energy and climate change, and the energy, the technologies we develop to capture the energy, which mainly covers marine and offshore wind, and the conversion technology or the machines would be power electronics and control, and the delivery is through power systems, smart grids, and energy storage, and so on. We also develop standards, documents for policy and innovation, regulations, and environmental assessment, and so on. So this is just a one-page view of what we do. We have world-class experimental facilities. The one that you see here is called flow wave, which is a circular wave current generation facility. It's a 25-meter diameter. Water depth is 2 meters. You can generate waves and tidal currents from any directions you want. Probably until you see this, it's difficult to appreciate the scale of the facility. You can see the man is walking here. If you scale this, his height with the other dimensions you see here, then you will appreciate the size of it. This is a world-class facility where we conduct our research. And also just to show you a quick view of how we test the tidal turbines in the facility. And here is another view showing a scale model of a tidal turbine. 3 of them, in fact, 3 of them are being tested in the flow wave. The reason we do this, we study the scale model, and then we translate them into the prototype, which would go into the real sea. So we test everything, its stability, its strength, its failure criteria, everything is assessed in a small scale laboratory study before they make into a bigger or prototype and then bring it to ocean. This is another concept of wave energy converter based on the polymers. And again, this is a new concept that we produced, we developed and tested here. And here is a small scale wind turbine, offshore floating wind turbine being tested in the same facility. I'd like to quickly introduce you. I'm not sure how many of you are familiar with the wave and tidal and offshore wind technologies, but I'm assuming that you have some understanding. With that, I'm just going to quickly tell you the concepts that have been developed so far. If you look at the tidal energy concepts, we have a barrage type, which is what we tried to investigate in India, the Gulf of Kutch and the Kampat and also Sundarbans area. We tried to look at a barrage type system through our research. We have the barrage, which uses the high and low tide for storing water inside the barrage. And when the water is released through a sluice gate and through a turbine, it produces electricity. And the second case is a horizontal axis turbine. This is similar to a wind turbine that you would see everywhere. It's a 3-bladed wind turbine, and it is fixed on a monopile immersed in the underwater. And here is a horizontal axis, vertical axis again. This is horizontal axis, which means it rotates about a horizontal axis. And in this case, it is a vertical axis wind turbine, and it would have again 3 or more number of blades. Another concept is called a open-centered or venturimeters. If you remember your fluid mechanics knowledge, I'm talking about the students, you would have studied about continuity equations and Bernoulli's equations, and all that kind of equations are being applied here. And the shape of the, let's call it as funnel or the tunnel, that helps to the water to accelerate. And when you stick in a turbine in here, it rotates and produces electricity. The other concepts are given here. This is a reciprocating wave, oscillating hydrofoil type. The hydrofoil oscillates up and down in a current, in a tidal current condition. And we also have Archimedes screw, which is a screw type of tidal energy converter. And we have the tidal kite, This is similar to the kite we play when we were kids. And when you put a kite underwater, under the tidal current, it makes a rotation, something like an 8. And that is being used to rotate a generator, and then that finally it produces electricity. And there are other concepts. You may be wondering, what is TRL? TRL is a technology readiness level. So the lower the technology TRL number, that indicates this is still in the experimental small scale studies. And the higher number, 9 or 8 or 7, indicates they have mature technology. Similar to the tides, we have wave energy concepts. We have oscillating water column. This was tried in India in 1994 or 95. And we have overtopping type device. The waves overtop the device, and the water is being collected in a reservoir, and then it is allowed to pass through a low head turbine rotating a generator producing electricity. And this is called attenuated type. There are many hinged sort of different parts are joined by hinges, and the hinges will act as a power takeoff system producing electricity. This is a point absorber type, and the point absorber type pops up and down, and when a power takeoff system is linked here, it would generate electricity. And this is an oscillating water surge. This is like a flap moving left and right. And when a pump is connected to the flap, it pumps out high pressure water to the shore. And when you have a turbine facility in the shore, then high pressure oil rotates the turbine producing electricity. And the submerged pressure, this is a concept. It works on when waves moves up and down or during the wave trough. There is a pressure exerted on the surface. The structure here pressed down, and during the trough, it pressed up. So the continuous up and down movement is being used here to produce electricity. And then a bulge type, this is like a floating, like sort of a snake. And the water is allowed to follow the wave profile. And at some point, a generator is fixed, and the water that is entrapped inside, when it goes through the generator, it rotates the turbine and produces the electricity. The other one is a rotating mass. And the heaving and swaying effect of a floater is being used here, and you have a rotating mass inside. And depending upon the motion, it's like an automatic watch. If you look at the automatic watch, you would see the back side of the watch, you would see a weight is rotating this way and that way. It's similar principle, and the rotating mass produces electricity. And now I'm going to show you some statistics. I have only 15 minutes, so I need to rush through. And if you look at the annual cumulative and tidal stream installation in Europe, it has reached 27 megawatt of tidal stream technology, which is, when I say tidal stream technology, it is using the tidal current, not the tidal range, which is another technology that is being used in barrages. So since 2010, Europe has produced about 28 megawatt of tidal stream. I'm sorry, it's not produced, it's been installed. Of this, a 10.1 megawatt is currently operating, and 17.8 megawatt has been decommissioned because they completed the testing stage. And you may see a drop down in 2019, 2020, and you know the reason why there is a drop down. That's the COVID. The electricity produced so far by tidal stream up to 2020 has reached 60 gigawatt hour, which is an impressive, very impressive number. If you look at the annual and cumulative wave energy capacity in Europe, and so far in the year 2020 alone, 200 kilowatt of wave energy was added. Overall, 12 megawatt of wave energy installed since 2010. and 1.1 megawatt is currently in water. 10.9 megawatt has been decommissioned as it completed its testing stage. And again, you could see a drop in 2020, 2019, and we know the reason clearly. And if you look at the number of devices installed, the tidal stream so far, it reached about 14 devices in the year 2015 or 2016. And now the number has come down. I don't want you to think there is any issue with it. It is nothing issue. It's just the COVID conditions. And in the future, I hope there will be more devices added to this. And similarly, wave energy. There are more than 50 devices have been deployed in 2016. And you can see the cumulative WEG development by the green curve as well. So it's a very high number. And it may be difficult to read the slide, but I'm just quickly going to tell you, this is basically the information that you've seen before. The tidal stream power production has reached in 2020 260 kilowatt. And you know, I'm not going to repeat this. This is the same information that you have seen, but the new information here, there are countries like China, USA, and Canada is adding the research capacities to wave and tidal energy industry. And they started producing electricity using these ocean resources. And if you look at the UK alone, you could see these are all the currently ongoing projects. The top one are for tides. We have a company called Magen. They are operating currently now in the Pentland Firth in Scotland. And the capacity is 6 megawatt. And you can see other companies. Some of them are floating tidal energy companies. And these 4 are in operation and 2 are under development. And similarly, if you take wave energy, there is motion energy. It is not 10, it's 100 kilowatt. They are under development and they are testing. And similarly, the M-Wave is another company they are testing currently. And there may be other companies also which are not on the list will be doing the test. Now, if you're wondering what's happening in India currently, the NIOT National Institute of Ocean Technology, which is in Chennai, they are developing technologies to harvest tidal currents, and it's a 5 kilowatt. It's a small machine, but still okay to begin with. And they have also developed a technology. NIOT developed a technology for wave energy, and they say this is operational. It could be. And they've also, I witnessed this one, the Votek power desalination plant when I visited NIOT. So there is more going on in India as well. Now some information about UK wind energy statistics. So the onshore turbines, so far there are 8,000 over, about 9,000 onshore turbines are operating. And you could see how much the capacity they have. It's 14,166. It's a very large number. And similarly, offshore turbines, there are 2,297 in operation. And they also produce a very high amount of electricity. Now, what I'm going to show is quickly, you know, we probably would have seen some of these videos before or some may not. And this is just to show you some additional information about some of the technologies that have been developed, tested, and so on. And what you see here is an area called Orkney Islands. The mainland UK is here. This is Orkney Islands. And that's where most of the wave energy and tidal energy developments are going on. The pink colored one are the sites allocated for tidal energy development. And the yellow color is for wave energy developments. There are many companies. If you are a developer, you make your device and bring it to this location and test your device. The device will be connected to an organization called EMEC, European Marine Energy Energy Center, and they have the facilities. You can hook in your device and test the ability of the device and the power protection of the device. So some of these technologies have been tested in the EMEC site, in here, and in here, and in here. And if you are wondering what is the current speed, tidal current speed here, the current speed reached up to 5 meters per second. This is a very impressive speed. 5 meters per second is a very fast current. And similarly, the wave height here, the significant wave height, if you are familiar with this term, the significant wave height has reached 7-8 meters in stormy conditions. And just quickly, I want you to see some of the current tidal current technologies. As I mentioned before, they are mostly based on 2-bladed or 3-bladed turbines. The companies named are given here: Alstom and Hammersfest, Atlantis. Even though they all have 3-bladed, the blade profile is different. The capacity is different. One may be 1 megawatt, another may be 2 megawatt, and so on. But this is for you to see that they are real. The development is real. And there are other type of devices. In here, what you see here is open hydro, which is the one I showed before, that technology. And a floating tidal technology, and this is the Archimedes swing, which I mentioned before. And also other twin-bladed technologies, and the company called Sustainable Marine Energy Innovations. The one good thing is all these technologies, or all these people are industry developers are working with us, or we worked with them. Many of them placed in Edinburgh, and they are developing the machines here before taking it to the sea. So therefore, we collaborate with them and they collaborate with us. So therefore, it is a learning between us. We learn from them, they learn from us. And some more pictures showing you the tidal current turbines developed in the past and tested. So if you scale up with the people standing here, you can get an idea of the size of the turbine. The turbines usually, the rotor size would be 12 to 16 meter, whereas the wind turbines will have anything between 90 meters to 200 meters. That's the diameter of the rotor. But we can't have that kind of large diameter in the ocean because it's water. There will be heavy force if you have a large turbine. And there are also small scale turbines developed for river applications. So the one of them is shown here, the Tucano turbine. And there are some more information, and considering the time, I'm not going to read out this to you, but just I want you to see this is developed for a 1.5 megawatt capacity, and it can operate between 3 meters per second to 5 meters per second current speed. And this was developed by a company called Magen. This is the one I mentioned. This is still in operation in the UK, producing electricity to homes. And the Nova is another small scale community level project, and 100 kilowatt, and it is also in operation. The orbital marine, this is like an aeroplane. You could see this is a floating tidal turbine. It's a twin-bladed turbine. There is another rotor here, one more rotor here. And if you want to watch the video, that's the turbine, and you could see how the speed of the tidal current. That shows the manufacturing process. This starts with the rolling up a steel plate and making into a circular tubes. Then it becomes a float. I will leave this PowerPoint with Professor Dhraj, so you can look at later on. This is being transported now, and that's the size. It's installed in the ocean. And this is in an operation. And again, that's how it would look like if you look at from an aeroplane. Just quickly pass for. In a stormy condition, the floater will be subjected to heavy wave loads and wind loads and so on, but it is still shown to be stable under those conditions. The wave energy devices, I've covered this before. There are basically 3 types of devices. They're called terminator, attenuator, and point absorber. And the technology, some of the technologies, I'm going to show the video. This is called a Promise wave energy converter. This was developed in Leith, just here in Edinburgh. And the one thing to notice here, this was developed by a student who has studied in Edinburgh and got his PhD from Edinburgh. And he became an entrepreneur and developed this. And most of I can see that another 3-4 device developers, they have studied in Edinburgh, who went on to develop their devices. And this is a Promise wave energy converter. I'll let you to watch the video. It's floating in the ocean. And the length of the device is 140 meters. The diameter is a 4-meter diameter. It's a very large, like a bus size. The nice thing to notice is a bird is sitting on it. So there is no environmental impact. I'll fast forward it. So that's the wave energy device. And you can see the hinges, the type of hinges here, that's where the power takeoff system is located. So the movement produces, the movement between 2 hinged bodies produces high pressure oil. The high pressure oil is then used to drive a hydraulic generator. Just quickly fast forward it. Professor Dhraj, is it possible to take an additional 10 minutes?
Yeah, you may please, yes.
Thank you. Then the next type is the oyster, which is a flap type. Again, this was manufactured in Edinburgh by our local students are involved in the beginning stage. And you could see the motion of the flap. And this was tested, all these devices were tested in the Orkney Islands. Oh, sorry, it's I should have fast forwarded. It's finished, I believe. So you could see it's not an easy thing to develop a device and test the device and to produce electricity. It's a very complex process. So this device is sitting on the bottom and swaying left and right to the waves. I think Professor Prashant or Professor Dhraj, you mentioned about biofouling. You could see the biofouling around the device. When you leave the device in water, that's what happens. Then another type of technology, which is called a terminator type, or wave overtopping type. You could see the wave overtops the device, and it is being collected in the reservoir. Then when it is sent through the Wells turbine or impulse turbines, then it gets used in the production of electricity. An oscillating water column device. This is a shore-based device, and when the waves approach the structure, and the water level inside the water column, inside the chamber of the OWC moves up and down, and that decompresses the air, entrapped air. And when the air is sent out or pushed out through a Wells turbine, then it starts producing electricity. Similarly, when the water level falls down, the air is drawn back into the chamber. This is a reversed process. And Wells turbine, we all know Wells turbine is made to rotate in one direction, whether the direction of the wind is from left to right or right to left. So this is a unidirectional rotating turbine concept. And when you build them within a breakwater, this is what happens. Sorry about the noise. So that's where the oscillating water column is built within this wall. This is in Spain, and it is still in operation, producing electricity. And you need large waves. You need large waves. And obviously this location is in the Atlantic, and Atlantic swells reaches this place. Therefore, it is a good site to be utilized for energy, wave energy production. And the one more device is called a motion device. It's a very small scale. And I'm proud to say that this was developed by my own PhD student. He did PhD with me 10 years ago. I went on to start his company. And this is now, they secured some multi-million pounds, and they are testing it in the ocean. So this is again a wave energy device, but it's a small 100 kilowatt machine, but still it's proven to be working. So the reason I mentioned my student name, the students are student when they are undergraduate or postgraduate, but once they have in their mind of the industry, getting into industry or technology development, then this is an example. That's where you end up. So don't give up your dreams or ideas. The another device, considering the time, I'm not going to run them, but this is a
Hello.
Yeah.
Yeah.
Did you say something, Raj?
No.
Oh.
Please continue.
Yeah, there are another 5 minutes or so, then I'll be done. So in addition to the wave and tide, we also have offshore wind. The one on the right-hand side, they are monopile-based foundations. On the left-hand side, they are floating wind concept. The floating wind concepts are used for deeper water, whereas the monopile types are used in shallow water. So the deeper water means more wind means more electricity production. And this is why the interest now is to move to deeper water using different technologies. The one you see here is called SPAR, semi-submersible, and TLP. These technologies are now being considered and being tested seriously. And on top of monopile type, you could also have a jacket type foundations, and you can put your turbine on it. This is very popular around Scotland now, and there are more development is going on. And this is again, as of now, there are 5 turbines in operation, floating wind turbines in the North Sea, and they produce electricity since 2017, the year 2017. And the North Sea is a very, very kind of complex sea. You see storms, very large waves, and heavy wind. but still the technology is proven to be surviving in extreme conditions. And here is a video of the floating wind. Just quickly pause. This is in Leith. Sorry, no, it's not Leith. This is in Denmark. So you could see, oh, that's gone. Sorry. You could see the wind turbine being towed to the location and deployed. The 5 of them are still in operation. Okay, so there are more concepts being developed for deeper waters. One is the semi-sub type and open pool type. The next is about my research. I'm going to quickly run. The key part in my research is to work with waves and tides and wind, which is a complex process, as I said before, especially when you have a tidal turbine underwater, you have waves, you have currents, and you have turbulences. So designing a structure to cope up with all these three is not an easy task. And this is why we need to do more research. And I'm going to skip these slides. These 2 slides tells you the basics or the mathematical background behind modeling waves and tides. I'll just skip them just to show you. This is a wave model I developed in 2014, I think, some 8 years ago. And here is the UK. And this covers the whole North Atlantic Sea. America is here. And we run the wave model using the wind input. This is covering the whole North Atlantic. You can see the wind getting stronger and stronger. And when you successfully construct the model and calibrate the model, validate the model, and run the model, this is what you would see. What you see here is the spatial variation of significant wave height. And you could see the wave height, the waves are starting from in here, Mexico, America, then moving towards Europe, UK, and Portugal, and that sort of places. And if you look at the red spot, that shows the significant wave height could reach up to 13, 14 meters, which is a very large wave, which is why we are interested in developing wave energy for European countries. And the model, if you are wondering whether to believe the model or not, here is a proof showing the measured wave height compared with the modeled wave height, and measured wave period compared with the model wave height, and measured wave direction compared. So before you develop the trust on the numerical model, you have to do this sort of calibration and validation, which is what I have done. On the wave power, we also produced the contour maps for wave power, and you could see the wave power reaches about 60, 75 kilowatt per meter for the UK locations, especially on these sites. This is where the Orkney Island is. The tidal model, we constructed tidal models for, if you watch this area, this is called Fall of Warners. That's where the wave current interactions are stronger, and the tidal currents could reach speed up to 4 meters per second or 5 meters per second. And that's the location I have tried to model to further understand what's going on there. And you could see the tidal current, the spatial variation of tidal current reaches more than 3 meters per second for the time period I have simulated. But these kind of numerical models tells us where the tidal current is stronger, so that the developer can go and take those area for developing the devices. So the numerical models helps us to locate the regions where future developments can be placed. And here is another snapshot showing over a very large area, you see consistently a current speed up 2.5 meters per second. That's what you need so that you can put hundreds of devices in this area. And I'm going to skip this again. This just shows you the turbulence. So that when you, anyway, to point out that when you have a turbulence produced by waves, current interactions, then the turbulence could be like it's a rotating mass of water. It's a very heavy rotation. So the reason we locate these regions so that you can avoid these hotspot, because that's where the water mass is not going to be or very unstable. Therefore, you are going to avoid the regions. It's like a tornado, little tornado underwater. So it's better to avoid these regions. Again, similar to the wave model, we have calibrated the model and validated the model. It shows the current speed and current directions between the model and measurements, and the models are able to reproduce the conditions, which increases our confidence in using the models for tidal and wave energy applications. Just going to quickly cover the research with India. As I mentioned before, I've been involved with three UKRE projects and several British Council funded projects. And the one I included here is with IIT Kharagpur and also with IIT Madras and University of Oxford and few other institutions in the UK. There's one other research with Jadavpur University, Cardiff, and IIT Kharagpur. This is a picture just showing a meeting. I don't think anybody that you know or here, don't think so. So what we did, we tried to model two regions, Gulf of Kutch and Kampat, and we wanted to assess the tidal energy potential with Indian researchers. And it came when we completed the simulations, we noticed that in the Gulf of Kutch, the current speed reached up to 2.5 meters per second, which is a very good current. This model was not calibrated or not validated because there is no measurement available, but the model shows that the currents, a high magnitude current, is possible at this location. But the researchers working with us, they also said they have noticed high currents, but there is no measurements to prove it. But this is just to show the tidal energy development is possible in Gulf of Kutch. And similarly, Kampat, and here also we noticed large current by up to 1.5 meters per second, not very large. But another point we noticed is the wave, the tidal range could reach up to 10, 11 meters. And that tells us this location could be, or this region could be a potential site for developing tidal barrages. And we also looked at Sundarbans, which is on the West Bengal, the region between Bangladesh and India. And we modeled this region. This is a United Nations UNESCO site. And there were many difficulties. No water depth available. Getting into the region itself, it's difficult because it's a mangrove forest and protected forest. And we have modeled these regions and we measured the water depth for two of the rivers using the equipments we bought through the project. And the University of Jadavpur did the work with IIT Kharagpur. And we modeled the region and we measured, we predicted the currents. The currents reached about 1.1, depending upon the period we modeled. And also, it is a seasonal, when there is a storm, when there is a cyclone, then it may change. But it tells us the current speed could reach up to 1.5 or 1. If you look at other locations, it reached 2 meters as well. Again, this is without calibration validation, but what the model predicted is true, then these locations are very good locations for developing tidal energy in the future. Again, there is another plot. So I'm going to stop now, but before that, I'm going to tell you what opportunities you have with us. We have been the world leader in marine energy research. I'm not sure, probably you may not have done anything yet on marine energy. If you have any interest, we can help you to develop into further. And we have research partners through the UKRE Royal Society British Council Global Challenge Research Fund. These are all some of the research opportunities or research calls often released. So if a call comes and if you think you could do or you could collaborate with us, then we can write a proposal, submit it, and get the funding. We can also exchange staff and student between us, but it needs to be done at the university level. We need to have an MOU or MOA to be agreed. And if you have a potential master students, they can apply to us for PhD and then they can work with us for the PhD. There are funding scholarships available for them. And if there is a suitable research identified, we can do joint PhD supervisions. And we can encourage visiting researchers like Professor Diraj did before. That's the opportunities available for us to collaborate. And I have to acknowledge the people listed here and who they are all contributed to the presentations. And I'm going to stop here. Thank you very much. And I'm really, really sorry for running too long and also running too fast. Thank you.
Yeah,
Any
thank
questions?
you, Professor Venugopal. With this, I open the floor for question and answers. The audience can post their questions in the chat box or the QA link that's provided.
Thank you. I'm going to open the chat box, but if anybody wants to throw a question, you can, please. I can't see any.
In the question answer QA box.
Right.
Yeah.
Where do I see this?
There are 3 dots, no? So.
Right. Okay. Right. Right.
Yeah.
Sir, may I read it for you?
Please, yeah, if you don't mind. Thank you.
This is a question asked by Professor Dheeraj Patil. How is the research span related to nuclear energy at EOE?
Right.
University of India.
Yes, yeah. We haven't really gone to, I mean, there are pockets of researchers working on nuclear energy, and the future will be nuclear energy and green hydrogen and that sort of research activities. But within our school or within our institute, we haven't started anything on nuclear energy yet. That's you need a specific expertise to do that, but there are other universities in the UK, they are looking at it. That would be the future task. We haven't started anything yet on nuclear. It's just a book level research. That's all we have done.
Okay. So there's another question from Dheeraj Patil sir again. Are tidal kites common nowadays? Is it in place in India?
No one tried in India, but there was a project funded by European Commission, and they looked at tidal kites. It is a known technology, but possibly it's better to explain this. When you see a 3-bladed wind turbine rotating on land, and you hear it is rotating fine, safely rotating and producing electricity, then the human nature is to look for similar technology. And this is why we went for a 3-bladed tidal turbines, and the 3-bladed or 2-bladed tidal turbines are common rather than a kite now. But the kite has been researched, and I don't have the details, but if you look for it, it may be there in some European Commission site. It was a concept developed and tested, but not to real scale.
Yeah, there's another question. What is the factor of safety that's used for the designs for an 8-meter typical wave height?
Right. Factor of safety in designing the structure or any other components, because a wave energy machine will have thousands of components. And therefore, there are standards like IEC, British standards, and American Petroleum Institute standards, they deal with designing the components. The components, when I say, there may be mooring, there may be foundation, there may be substructures, and so on. So each component will have a factor of safety. So there is not a single factor of safety I would mention, because each component is given a different cushion factor. Sorry, I can't tell you a single factor.
There's another question which indicates about what is the grid size you're using for the numerical approach that you have that you adopt for the study?
That's a very good question. If you are doing a tidal numerical model, then we have to satisfy the CFL number, and which would be usually 0.5 for a tidal model. For a wave model, it could be up to 0.8. So in order to satisfy the CFL number and also to capture everything that is going on there, we have to go for a very finer scale meshes. So the mesh size I used at the device location is 10 meters, and then it got bigger and bigger. So the smallest mesh size is 10 meters. Side of the triangle.
Yeah, I have one question, sir, Professor Venugopal. What is the variation in the periodicity of wave energy that can be, used for generation of electricity?
Okay, so if you consider, there is also, before that I will mention about India. In India, there is a place in Trivandrum in Kerala. That's where IIT Madras developed the first ocean energy converter, which is an oscillating wave energy converter. And at the time I was a student in IIT Madras, 1994 or 1993. And this was a 150 kilowatt machine. It was built in Trivandrum and tested, but then it was given up. The one reason could be there is not a consistent amount of energy that you would get from waves. But whereas if you come to UK, the waves are very large here. During the winter time, that's when we get the storms from our hurricanes from both. We are located between Atlantic one side and North Sea another side. So we are bombarded by both the seas. So the wave height could easily reach 8 meters to 18 meters. Or 2 meters to 18 meters, let's put that way. So during the storm conditions, it's normal to see a large wave, one single wave reaching a wave height of 25 meters. Very normal to see a 25 meters wave. That's not possible in India or in Indian Ocean. The storms, now due to climate change, they are getting bigger and bigger. Therefore, there will be more waves. But when you go to winter time, summertime, the wave height is small. You don't see that many storms developed. Therefore, the wave height is, something like 4 meters. It's not still smaller. So we have a variation between winter and summer time. Winter time, you get more wave heights, therefore more energy protection. Summertime, less wave height, therefore less energy protection. But this is good for us because as a country, the UK need more energy during winter to heat up the homes. And also it gets darker. It gets darker by 3 o'clock or before 4 o'clock, it becomes dark. So you're not having 12 hours like you have in India. We have 14 hours, 16 hours dark. Therefore, we need more light during the winter time. So that is nature itself nicely matches with it. So winter time, more energy produced. Summertime, we don't need because we have sunshine for 14 hours or 15 hours. Therefore, we don't need much electricity during summertime. And that matches with the nature itself. So I don't know whether it answered your question, Professor Prashant. But
precisely. Yeah, you did, sir. Yeah. Professor Venugopal, one more doubt that I have is because these ocean-based energy sources are slightly located away from the load center, do you have certain issues regarding the transmission of energy that you generate to the load point?
The nearest devices, I mean, if you look at the bathymetry, the sea depth around UK, it's not like India. You don't have a mild slope. You have for about 10 meters, in some location within 5 meters from the shore, you get 300 meters depth. Suddenly the depth goes down. It's not a mild slope. The continental shelf region I'm talking about. And therefore, some devices can be located very close to the coast. For example, the flopping device I said that was located in a 12 meters depth, and that was located within half kilometer from the shore. Therefore, the transport of electricity is easy, or in this case, it was transporting the high pressure water to the shore, and then it was used to run the turbine. But there are other devices, deeper water, and they are located about 2 kilometers or 3 kilometers from the shore, but they produce electricity at the spot itself. It's only the cables that transport electricity to the shore. So the power is produced in deeper water and transported to the shore by power cables, similar to the offshore wind turbines. They produce electricity 30, 40 kilometers away from the shore, and it is transported through power cables. Therefore, it is not an issue. It's an expensive process because you need to lay power cables for 30, 40 kilometers. And there may be energy losses within the power cables, but other than that, it has been proven to work very well.
So one last question from my side. We also hear about the ocean thermal energy conversion devices.
Yes.
How do you find the potential for these systems?
That's very good for tropical countries like India. The NIOT, National Institute of Ocean Technology, they tried that. And also other locations in Chile and that kind of tropical, the countries close to the equator, they are very good for that. Because you would have very low temperature water. And say if you take a 500 meters water depth, you would have near zero temperature at the bottom and 25, 30 degree at the top. So therefore the temperature variation could be very much used for the VOTEC technology that you mentioned. Whereas in our country, it is always the temperature is 2 degree, 3 degree, 4 degree in winter. And in summertime itself, very rarely it reaches the water. I'm talking about the water temperature reaches about 18 degree or even 20 degree. So from 0 to 15 degree, this technology won't work successfully. Therefore, it was not tried in the UK. It was tried, but it wasn't successful. People thought it may not be sustainable. But it may be sustainable, or it has shown to work very well in India. So for Indian scenarios, this is a good technology to think about.
Okay, may I invite any other audience if you have questions to Professor Venugopal?
If you are a student, don't hesitate to ask questions. I'm happy to receive questions from you.
Okay.
There is also one thing to mention here, and I want you to think about. I'm talking about the students and also faculties. India has a very large coastline. It's more than 5,000 kilometers or 6,000 miles or whatever. I don't remember exactly. And it's got waves. The waves may not be large all the time, but there are locations where you can get large waves. But yet, the development of wave energy technology is being slow. Similarly, as I mentioned, there are tidal energy potential for some locations in the UK where you can think about developing tidal energy. On top of that, wind energy, offshore wind energy is good. I mean, I've seen people trying wave energy. I've seen people trying tidal energy in India, but not offshore wind. So you may think about it at IIT Dharwad. thinking about developing, in addition to the solar energy that you mentioned, think about tidal offshore wind. That's another area that's going to be the future. Edinburgh will help if you need any technology transfer or any knowledge transfer. That's all I got to say.
Thank you, Professor Venugopal, for your fantastic talk in spite of some technical glitches we had. So on behalf of IIT Dharwad and all the participants, I extend a heartfelt thanks for Professor Venugopal. We also thank the audience for their interactive discussion. Thank you, Professor Venugopal. I would also request the audience to join us on 4th April 2022 for another talk by Professor P.S. Lee, Executive Director, Energy Studies Institute, National University of Singapore. So that would be talk number 6. We would be hosting under the platform of trees. I now hand over the session to Professor Dheeraj to take over.
Thank you, Professor Prashant. Thank you, Professor Venugopal, for your time and this talk. It was really enlightening. Thank you.
Thank you very much, Professor Prashant and Professor Draj for inviting me to give this talk. Unfortunately, we had some issues in the beginning, and it was a long presentation, and at some points I had to rush through. My apologies for rushing through, but I from my heart, I thank you all the people on the call, and also for organizing this webinar. And I would be very happy to collaborate with you, even though you are a new IIT. I'm very happy to work with you. And if you see any collaboration opportunities, please let me know. I will do the same thing, and we will work together and help to develop your institute. Thank you so much.
Thank you.
Thank you, Professor. Thank you.
Thank you all. Bye just now. Bye-bye.
Bye.